I think so. Perfect, Philip. Thank you. Okay, so I'm gonna promote you to a panelist. Okay, so Philip, okay, Philip, there you are. Hi, Philip, how are you?
Hello, I'm fine,
Hi.
thank you.
How are you? Thank you so much for helping me today.
No problem.
I guess we haven't met before, but it's nice to meet you. I guess. Thank you. I guess today what I'm going to be needing for you is to stay alert on the Q&A, and if there are some like simple to answer quick questions that you think I mean, I'm sure that you will be able to answer any questions, but I'm more interested that if there are quick questions that people can get a lot from just reading your answer, then you go ahead and answer them. But also, like, if there are maybe a little bit longer and typing the answer would be long or something, just feel free to interrupt me at any point, and I'll answer them.
Yeah, that sounds fine.
Okay, awesome. Thank you, Philip. Okay, hi everyone. So I guess there's this is the third week that we're gonna be doing this Python4STEM series. I am really happy to be here. I'm Ivan. I will be I guess the main panelist today, and I guess I will introduce myself. I am a PhD student at the University of California, Berkeley. I study physics. More precisely, I'm in the field of high energy physics and nuclear theory, working on lattice gauge theory, which is a computational approach towards understanding part of the standard model of particle physics, namely QCD and the theory of gluons. I guess to tell you a bit about my trajectory, I'm from Colombia. That's why my name has that little accent on the A. That's so that my name is Ivan, not Ivan or Ivan, or the accent puts the stress on that A. I did my undergrad in Colombia, and then I did a master's degree in Brazil at the IFT. I did my undergrad in the Universidad de los Andes. And then I did another master's degree in Canada at the Perimeter Institute, and then I landed here at Berkeley. And today we're going to be talking about calculus. So I hope that everyone is excited about that. So maybe we should just go ahead and start. Yeah. Figure this out. Awesome. Philip, can you just give me a thumbs up that everything is being seen? Okay.
Yeah, everything's fine.
Awesome. Thank you, Philip. Okay, great. So today we're going to be talking, it says differential equations. We will not be talking about differential equations, but we will be talking about rate of change in calculus. Okay, and I maybe as a matter of introducing the subject, a common threading theme across these lectures has been the fact that programming can be a really powerful tool for all the STEM disciplines. And sometimes people have the incorrect idea that programming can be a clutch, and that computers can be a way of getting around doing some difficult things. And that is really wrong. Computers are a tool that, to implement in an effective way, demand that we understand very deeply not only the concepts or both concepts and mathematical tools involved in any theory that we want to study or in any application that we want to study. And in particular, we need to understand the mathematics of whatever we're studying really well if we want to be able to translate whatever system we are studying into a form that will be understandable by a computer. And arguably the most important mathematical tool, maybe other than linear algebra, that we use in STEM is that of calculus. And some of you might have some experience with this before. Some of you might have never seen calculus before. So we're going to start from the very beginning. And we're going to focus on developing intuition and what calculus is all about. And we're going to, rather than focus on how to do stuff on a notebook, sorry, on a notebook, I don't mean a Jupyter notebook, I mean on pen and paper, we're going to focus on how to use computers to help us develop some intuition around calculus. If you have questions at any point, please feel free to put them in the chat, and Philip will help me answer, but also maybe Philip will pass on some of the questions for me to answer live on the stream. Okay.
Adriana Beniecki is on the participant side. She's another TA for the course.
Oh, awesome. Thank you. 1 second. Oh, wait, can you do that, Philip? Is that?
I don't think so. I think that only the host can do it.
Okay, let me really quickly. This is Adriana, right?
Yeah.
Okay. Did that work?
I think so, yeah.
Okay. Hi, Adriana. Thank you. Thank you for helping us today. Is there anyone else that I should be promoting before I start? Okay, I can't
see anyone else.
Right. Okay, good. Awesome. Okay, let's then go ahead and start. Okay, so so how are you all doing? Are we happy with coding? Let's get into this. So today we're gonna, as I was telling you, we're gonna be talking about calculus. And I guess this image sound like shows a lot of things that people think about when they think about calculus, and some of it might look very intimidating, but we're going to see that it's actually a really beautiful and really intuitive and really wonderful subject. So let's go for it. There are two people that calculus is usually ascribed to, and those two people are Isaac Newton and Leibniz. And both Newton and Leibniz did independent work on the foundations of calculus, and sort of even though they weren't the first to think about the problems that calculus addresses, they were definitely two people that did some very important leaps on what calculus is all about. Newton in particular, you might know because of Newton's law. So Newton was really important for the development of physics. Although the notation that we use nowadays for calculus is mainly due to Leibniz. And calculus is broadly, very broad terms, divided into two areas. One of them is differential calculus, and the other one is integral calculus. So differential calculus is the study of the change or the rate of change of quantities. And we're gonna see in quite some detail what this rate of change means and how it relates to slope of curves, what its graphical interpretation is, and so on and so forth. This differential calculus is what we're going to spend our largest time in. And the reason is fundamentally that differential calculus is something that we call local. It has to do with local properties of these quantities. On the flip side, the other side of calculus is called integral calculus. Integral calculus is very geometric subject in calculus. It has to do with computing areas. Sorry. And precisely because it has to do with computing areas, it is a global subject. So it has to do with very global properties or whatever we're studying. Oh, I think somebody is commenting that whether the stream is lagging. Can I get a thumbs up whether that is whether we're good or?
The stream is always going to be about 3 minutes behind.
Okay. Okay. Good. Okay. Okay. Good to know. Okay. So yeah, so integral calculus is a more global subject, and because of that, it's actually a little bit harder. So one of the things that we're going to see is that differential calculus is a very straightforward thing in the sense that we can do a lot of analytical results, analytical meaning with pen and paper. And there's sort of some techniques to just solve the problems of differential calculus in a straightforward way. Integral calculus is quite different from that. Integral calculus, there doesn't exist such techniques, and in general, the problem of solving what integral calculus is about, which are called integrals, is a lot harder. Because of that, we're actually going to be spending a lot less time thinking about integral calculus in this lecture today. Okay, so since we're gonna stand on the shoulders of these two giants, let's move forward and dive into our subject. So let's first of all set up some notation, and this is gonna be a hard part of today that I want you all to make sure that we're all on the same page. So there is this. We're going to be studying quantities that we're going to call f, which depend on some variable that we're going to call x. So that variable x, we're going to call the independent variable. We're going to think of x as a variable that we can tune. And f of x is the value of f when x takes the value x. Okay, so for example, when x takes the value x1, f might have some value, f of x1. Later, x might have a value x2, then f is going to take the value f of x2. When we change the value of x between x1 and x2, the difference between those two values, x2 minus x1, which is the change in x, we're going to call delta x. So that is the distance between the point x2 and the point x1. Now, I know I'm setting notation right now. This is sort of the generic notation we're going to use to think about calculus. But in actual examples, it might be that x takes another name, right? So, for example, we might want to think of time as the independent variable, and because time starts with t, we might call that variable t instead of x. And to make everything more confusing, we might want to think of position as a function of time. So the position at a given time, so position will be the dependent variable. And we usually give position the name x. So x will sometimes be playing the role of the function f, even though here x is the independent variable. So be very mindful of that sort of notation flips that we're going to do, because we're going to do them because they're very common in the subject, but they're definitely something that can produce a little bit of confusion. Okay, I saw someone raise their hands briefly, but that disappeared. So I guess that was solved. Okay. So moving forward, as I was telling you, our main example is going to be that of motion. Okay, and we're going to be interested in studying questions regarding motion. So for example, a question that we might be interested in studying is, where is the object? That question is something that we call an observable in physics. And observables are described by certain quantities. And in this case, that quantity is going to be the position. That's what the quantity that we're going to use to answer that question, where is the object? We can also ask, how far has it traveled? And there are going to be quantities that are going to help us describe the answer to that question. And some of them are going to be, for example, displacement or distance, which colloquially might seem like the same word, but in physics, they have very different meanings. We might also ask, where is it going? Or how fast is it going? And that is the fundamental question that differential calculus is going to help us answer. And the answers are going to be in the form of quantities such as the speed or the velocity, which once again, colloquially, we might think as the same thing, but in physics, they have a very definite difference between them. We might ask also, is it speeding up? Are we going faster? Or is it slowing down? Are we stopping? Or neither? Is it staying at the same rate of change? And there's going to be a descriptive quantity associated to that called acceleration. Okay, so let's start studying our first question. Where is an object? And let's start studying the quantity that we're going to use to answer that question, namely position. Okay, so position. In order to describe the position, we're going to set up a reference frame, and we're going to, for now, just think for today, we're going to think in the simple. Okay, so this is a general rule about learning stuff. When you're learning stuff, you always want to understand the simplest examples first. That is the best way of going around things. So today, we're going to study the simplest example where the world is something that we call one-dimensional, meaning the world is a line. Okay, and we can either move to the right on that line, or we can move to the left on that line. To describe the position on that line, we're going to set up a reference frame. And what that means in the case of a line is simply that we're going to choose one point in the line to be a special point, and we're going to call that 0. We're going to measure the position by, let's say, of a particle over here by saying how far away is it from that special point that we decided to call 0. That special point is called the origin. And we're also going to not only say how far away we are, but we're going to say the number as a positive number if we're to the right of the origin, or we're going to say it as a negative number if we're to the left of that point. So that quantity, that number, which can be either positive or negative, and which describes the distance from the origin, that's what we call the position. Okay. So in this example that I was telling you about, where the point is over here, that position will be 2 meters from the origin. And this is the fact that there is a plus sign here. Of course, we don't write the plus sign, but this is a positive quantity in the case of the direction. Note something really important. This is measured in meters. Saying that the position is 2 is completely nonsensical. It doesn't make any sense to say x equals 2. We need to, but x is something that we call a dimensionful quantity. It's a quantity of length, and therefore it has to have units of length. And I can choose whatever units I want, right? Instead of saying that it's 2 meters to the right, I could have said it's 200 centimeters to the right. And 200 centimeters and 2 meters are exactly the same object. And 1 meter is exactly the same object as 100 centimeters. Of course, we could also have an object like this one, which is also 2 meters away from the origin, but to the left. So there we say that x equals minus 2 meters. Okay, let me off. Now, here we're gonna have the opportunity now of saying how far has it traveled, right? And there are 2 objects that we can use to describe how far it has traveled. We can use distance and we can use displacement. Now, the distance is the total ground covered while traveling. Okay, and we're gonna see some examples of that. The displacement, on the other hand, is a vector. Vector meaning that it has a magnitude and a direction, just like position before, that tells us that what the position is between where we ended and where we started. Okay, so let's see, for example, a very simple example of how these are different. So in this first example, this blue dot has a displacement of 2 meters from the origin, while this blue dot has a displacement of -2 meters from the origin. However, the distance of that a particle goes through when they travel from the origin to here along a straight line, or when they travel from the origin to here, is in both cases 2 meters, right? So distance has no sign because it doesn't have a direction. And we're going to see that this can actually be a lot, it's not as simple as the distance being just the absolute value of the displacement. So let's see some examples of that. So let me just ask you a question. We're going to take 3 minutes to answer. So a car moves 72 kilometers to the right and then reverses direction and travels 120 kilometers to the left. What is the displacement of the car versus what is the distance traveled by the car? So I'm going to give you 3 minutes before we answer this question. Okay. So let's take a look at the first question. So when we say the car moves 72 kilometers to the right, that means that the car goes from here to here first. So let's go to the next slide. So that is delta x1. And when it travels 120 kilometers to the left, we mean that then from here, it goes all the way to here, right? So if this distance is 72 kilometers, and this distance is 120 kilometers, then this distance right here has to be 120, which is the size of this big arrow, minus the size of this little arrow, which is 72, right? And then this distance right here is 48 kilometers, but it's 48 kilometers to the left, right? So the answer is minus 48 kilometers. On the other hand, the distance traveled, well, from here to here, there was a ground of 72 kilometers that was traversed. And from here and here, we had 120 kilometers that were traversed. So yeah, the sum of those two is 192 kilometers. So the point here is that displacement is not only the distance, it's just the absolute value of displacement, but there are truly different quantities. Okay. Okay, good. So we've seen position. Now we want to take a look at speed. So speed answers the question, so how fast are we moving? And we have 2 points in time, let's say an initial point t1 and a final point t2. We're going to define the average speed between those 2 points to be the total distance traveled between those 2 points. So the 192 kilometers of the previous slide divided by the time elapsed So notice something, distance is always positive. So this average speed will always be positive. Speed is not a vector. Speed is just a scalar quantity. It's just a number, a positive number, divided by the time elapsed. And now I also wanna notice something very special about this formula. If you fix the time elapsed, right? So we take this denominator as a constant, the larger the total distance traveled, the higher the speed will be. Okay, and that hopefully makes some intuitive sense, right? The more distance, the more ground I cover through in a given amount of time, then the faster I'm going. On the other hand, if we fix the numerator, that means if we fix the distance traveled, the smaller the time elapsed is, then the higher the speed is, which means that if I want to go from point A to point B, the less time it takes me to go from A to B, then the faster my speed is. On the other hand, velocity is going to be the displacement divided by the time elapsed. That will be the average velocity. And this is now a vector, right? Because it will have a magnitude. And as we saw, that magnitude does not have to be the speed, because displacement, the displacement, the magnitude of the displacement does not have to be the distance covered, but it will have a magnitude and it will have a direction. It is either to the right if we're going towards the right, or it's to the left if we're going towards the left. And now, so far we've seen average quantities, and I want to just start building some intuition for what this speed means. So imagine that at 15 seconds, we're at position 60 meters. And at 30 seconds, we're at position 120 meters. Which means that the distance we traveled, or the displacement vector, is 60 meters to the right, which in this case is 60 meters positive. And the time elapsed was 15 seconds. Now you might see this difference minus this difference, this size here divided by this size here is what you might recognize as the slope of this straight line that we drew here. Okay, so we see that speed has to do with slopes. And this might, for example, be the path that we took in this motion, right? So we started at 0 at time 0, and then we moved to 60 meters at 15 seconds, and then we moved to 120 meters at 30 seconds. And we can also read, for example, that at 5 seconds, we were around here, which is around 20 meters. Okay. So precisely this distance right here is the change in the horizontal direction. And this distance right here is a change in the vertical direction in the graph. And that quotient that we were calling the velocity is precisely this slope. Notice that velocity has units of meters divided by second, because position has units of meters and time has units of second. Okay, now, so far, this is another example of some possible motion. It's a more complicated motion because it goes in a curved trajectory. And so far, we have focused on two instants in time, t1 and t2. And we have said, for example, that the average velocity is obtained by drawing a line between the two points and computing the slope of that line. That is, computing the quotient of the change in x versus the change in time. However, that is not a good estimate of how fast we're going at t1. For example, one might consider doing a thought experiment where we, instead of thinking of t2 being over here, we might think of t2 being all the way over here, so that we have, for example, a line that goes from here to here. As you can see, from here to here, the displacement in delta x is not very large, right? But let's do another example. Let's do t2 over here, right? So between here and here, delta x is really large, which might make you think that over a t1, the speed was really fast. But as we can see, the actual slope of the curve over here is not very large, which means that at x1, we weren't going very fast. We were changing position very slowly, and what happened was that around here, we started going faster and faster and faster, and thus changing our position faster and faster and faster. And that's why we arrived at this point. So we want to solve that. And in order to solve that, what we're going to do is take the intervals of time to be smaller and smaller and smaller. So we're going to bring T2 closer and closer and closer and closer to T1. And that's what this figure right here is doing. So as you can see, this line, the point T2 is getting closer and closer and closer to T1. And thus this line that we're drawing over here is getting closer and closer and closer to this line right here, which is the tangent line at P1. The slope of that line is what we're gonna call the instantaneous velocity, okay? And that we write fancily in mathematics as the limit of the slope of all of these lines as the difference between T1 and T2 goes to 0, okay? And then fancily, what Leibniz used as a notation for this is dx dt, which reminds us that this is this dx, you should think of it as a delta x, but that is infinitesimally big, which means that it's really, 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 really small. And this dt is the same thing. It's also changing time, but also really, 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 really small. And that is the concept of instantaneous velocity. Okay, now we're gonna try to develop some intuition about this. Maybe before that, let me just open some time for questions. Does anyone have any questions? Okay, so let us study a problem called the harmonic oscillator. So that might sound a bit scary. You'll be glad to know that this is the favorite problem of physicists. It's the only problem we can solve. So if you do a career in physics, you will find that a career in physics is just an endless sequence of harder and harder and harder versions of the harmonic oscillator. So today I want to study the harmonic oscillator. What is the harmonic oscillator? Is the simplest thing you can think of. It's a box on a spring that is oscillating. And so we're gonna have a wall, and attached to that wall there's gonna be some spring which has a box attached at the end of the spring, right? So the box is gonna be in some stable configuration like this one. And then if I push the box down, what do you all think is gonna happen? Well, the box is gonna start oscillating up and down, up and down, up and down, right? We're going to be working in an idealized setting where there is no dissipation of energy, which means that this box is just going to go up and down, up and down, up and down forever and ever and ever, which would require a really, really good spring. And we're going to think that we have an ideal spring that does that. Of course, in real springs, the box will go up and down, and will be the amplitude of that oscillation, which means the distance between the point of equilibrium and the farthest it goes down is going to be is going to start decreasing as time goes by until at the very end the box is going to stay still. But in this idealized way, there is a function that goes up and down, up and down, up and down, and that function is called the cosine function, right? So so this is going to be the motion that this is going to take, and perhaps when we study differential equations, you guys are going to see where this equation comes from. But for now, let us just make sure that we understand what the objects in this equation are. So this is x, the position, as a function of time. Remember, the cosine is a function that goes between 1 and -1, right? So a is the biggest x is ever going to be, which is when the cosine is equal to 1. And and minus a is going to be the smallest the farthest down it will ever go, which is when the cosine is equal to -1. On the other hand, this big T right here is called the period of oscillation. That is the time that it takes for our box to go from the up position down and all the way back up. That's called the period of oscillation. And you can see that that's the case because the cosine goes from the top all the way to the bottom and then back to the top in 2 pi radians. So you can see when little t, when time is equal to the period, the 2 periods are going to cancel, and we're going to have the cosine of 2 pi. So that we're going to be back at the top. This is the plot of this, and in the files for this lecture, you can see the code where I built this plot. I'm not going to focus too much on this plotting scheme since you studied plotting last time, but you can play around with that code and see how this code is built. And notice something fundamental. I am not plotting x here. I'm plotting x divided by a. That's something that you're going to see done a lot in numerical plots, which is that whenever possible, we're going to try to plot the dimensionless quantities. And that's because computers understand a lot better quantities that are pure numbers that have no dimensions. And since x has units of meters and the amplitude has units of meters, their quotient is unitless. It is dimensionless. Similarly, instead of plotting time here, I'm plotting time divided by the period. And therefore, we see that the particle goes from the box goes from up, down, and all the way back up in 1 t divided by t, which means that when the time has gone through 1 period. Similarly, you see that the highest position is 1 and the lowest position is -1, but remember this is x divided by a, which means the highest position is actually a, and this is actually -a. So if you want, what we are doing is measuring x in units of a and time in units of the period. And we can see, and there's also code for this in the materials for this class. We can, here I'm plotting the actual motion of the spring, and I just want you all to see how that motion is shown by this dot moving across the plot. So hopefully this will help you build some intuition to what these plots mean. Right. Okay. See it going all the way back down, sort of slow, comes to a halt, and then it goes all the way back up, goes really fast over here. It's going really, really, really fast, and it starts slowing down, slowing down, and it comes to a halt, and it starts taking up speed, and it goes fast. It's going super fast right now, and then it comes to a halt, and it stops all the way at the bottom, and it sort of keeps going like that. So as you have noticed in that description, I used words such as speed, fast, slow, coming to a halt. Now we're going to give a rigorous interpretation to all of those things. And as we said, the rigorous interpretation comes from this notion of velocity, which was the slope of the curve. So before we do anything about taking any derivatives or anything like that, let us plot this slope. So at the beginning, this particle is, we can see the slope here at the top is purely horizontal, which means that the velocity is equal to 0. Right? Now let's see how that slope changes. Becomes negative, negative, negative. It's very negative, but it's constant, but very negative. And then it starts quickly goes through 0. Oh, sorry. Let me try that again. Oh yeah, okay. Starts going down, it starts going down, and it's negative, and then very quickly it shifts from negative all the way to 0, and then all the way to, I'm sorry, let me open my controls. And then it goes through 0, and then it becomes positive, right? And then it is now positive. And then it quickly becomes negative. It goes through 0 and becomes negative. Now it's negative and constant. And then really quickly, it goes through 0, the thing goes to a halt, and then it becomes positive, and the thing starts going back up. Okay, good. So that's the slope. Now let us go ahead and keep moving. Now we can plot the velocity. So as we saw, the velocity is the slope of this line. So I'm just plotting the slope, and you see the slope starts at 0. Then over here, we saw the slope is going to be negative. And indeed, the velocity over there is negative. You can see this velocity is negative. You can see that over here, as I told you, it's going the fastest it can go. It's the most negative. And indeed, the velocity over there is very, very negative, right? And then it starts slowing down, but it's still negative until it reaches around here, where the velocity quickly goes through 0, right? Which was over here. And here it becomes 0. And then it transforms into being positive, right? The slope here is positive, which corresponds to this numbers now being positive over here. So let's see that in the video. You see the velocity is negative. Then it becomes very, very negative. And in here, it goes back to 0. But it goes to 0 only for an instance. You see how it moves so fast from here to here? And then it becomes very positive. And then again, it's going to change from positive to negative, going through 0 really, really fast. And then it's negative. Negative here, not changing a lot, right? Between here, it doesn't change a lot, right? And then it goes really, really fast from here to here, right? Going through 0, so on and so forth. Okay, so hopefully that will have helped build some intuition. Let me maybe stop for a second to answer some questions in case this videos have produced some questions while I let the video run again. Okay, awesome. Now maybe I will ask you all to take a second and ask, does this curve seem familiar to people? Are people willing to adventure and to guess what curve this is? Give some time to people to ponder on that question. Yes, thank you very much. Yes, it is minus the sine of x. Awesome. Okay, great. And we will check that later. Okay, so let's move forward. Now, velocity itself is a function of time, right? As we saw here, we plotted velocity as a function of time. So there's nothing stopping us from wondering, how does the velocity change? In other words, what is the slope of this curve? And we can go ahead and define something like the average acceleration, meaning the slope between 2 points that are separated in difference at a definite time. So for example, let's imagine that a car is moving at 15 meters per second at some initial time. And then it slows down to 5 meters per second 5 seconds later. So what is the car's average acceleration? Well, the final velocity is 5 meters minus the initial velocity, which is 15. That gives me minus 10, divided by the change in time, which was 5 seconds. So divided by 5, and minus 10 divided by 5 is minus 2. So that would be minus 2 meters per second squared. Notice something, the acceleration is measured in units of meters per second squared. And that's because the velocity was meters per second divided by time, which is another second. So we get meters per second squared. So it's a dimensionful quantity again. Notice also that the acceleration is a vector, meaning that when we're slowing down, when the velocity, I shouldn't say slowing down. I should say when the velocity is decreasing, and notice that is different from slowing down. For example, you could be speeding up, but to the left, and that would also be the velocity decreasing. Then the acceleration is negative. And we say the object, well, the object would be decelerating if the speed is going down, but you could also be accelerating, but to the left, and then the acceleration would be negative. Okay, let's stop to check ourselves. So if the acceleration is 0, does it mean that the velocity is 0? Yes, no, or maybe? What do we think? So I'm seeing some answers. Does everyone agree with those answers? Yeah, so I'm seeing the answers. Everyone seems to agree that it doesn't, and indeed that is correct. No, it doesn't. What the acceleration being 0 means is that the change in velocity is 0, not that the velocity itself is 0, which means that the velocity is a constant. Okay, and that is what we're seeing right now. Notice something. Well, okay, maybe we'll get a chance to go back to this question later. Similarly, we can define instantaneous acceleration, right? By instead of taking the slope between 2 definite points in a velocity versus time plot, making one of the points infinitesimally close to t1, and that's what defines the acceleration, and that is itself a derivative. Okay, so that works in exactly the same way as the position as the position did, as a derivative of the position did. So the acceleration is now the derivative of the velocity. So now let's play the same game that we were playing before, right? So I have position and velocity, but now let me plot the slope in the velocity graph as well. And let's try to figure out what the acceleration is. So we see the slope, first of all, starts out negative, which means the acceleration is very negative at this point, right? And then it quickly goes through 0 and it becomes positive, right? And now the acceleration is positive, right? So the acceleration is towards so that the particle is moving to the right. Then the acceleration becomes 0, and now the acceleration becomes negative, which makes the velocity move faster to the left. And here, that same negative acceleration makes it slow down, and then it becomes positive, which means it starts speeding up like this. And then it starts slowing down as the acceleration becomes negative, and then the velocity starts going in the opposite direction. Okay, and now we can also plot the acceleration. I'm sorry that this is kind of distorted, but I did that compromise to fit it all on the slide. So now we can plot the acceleration curve. Let's understand this curve in terms of what's going on the physical spring. Okay. And I'm going to use a sleight of hand. Instead of talking about the acceleration, I want everyone to think of the force the spring is doing on the box. Okay, so at the very beginning, the spring is completely compressed, right? The box is all the way at the top, right? So the spring is completely compressed, which means that the spring is pushing down a lot, right? And you see, this is very, very much down, right? This acceleration is at its lowest, right? So the spring is pushing really, really hard. The spring is pushing really, really hard. And as the spring goes through the point of equilibrium, the spring stops pushing and the acceleration went through 0. And now the spring is getting stretched. So now the force is going up. The spring wants to restart itself. And that's why the acceleration was positive there. And then, so now we see, so the spring is pushing down, it's 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 getting relaxed, it's going to 0, it's getting relaxed, relaxed. And then it starts pushing up, pushing up, pushing up. It's too stretched. We're very positive right now. And then it starts relaxing. It stops pushing. That's why we went through 0. And it starts pushing down again. And that's why it's very negative here. So you can see I can read this acceleration plot by thinking of force, of what the spring is doing, instead of thinking about the motion of the particle. And that is the concept of Newton's second law. which you studied last class, right? Where you saw that force is equal to the acceleration up to a constant, which is given by the inertial mass of the particle. Okay, awesome. So hopefully this will have helped you build some intuition. And now, in a normal calculus class, what you would learn now is how to take the derivatives of a bunch of things. Okay, so you would look at a bunch of functions, and you will learn how to take the derivatives. And something that is really nice about differential calculus is that there are rules for taking these derivatives. So this is something that for a lot of functions we can do by hand. You should memorize this at some point, or when I say memorize, really what you should do is memorize these plots, okay, or memorize these physical ideas, right? So now for example, you saw that the derivative of the cosine function is minus the sine function, but I don't want you to remember this. What I want you to remember is, okay, if my spring starts at the top, like a cosine does, which starts at the top, and then it goes down, how does the velocity behave? Well, at the top, I have 0 velocity, right? So it looks like a sine, and then the velocity becomes negative as it starts going down, so the sine becomes negative, and so on and so forth. So that will help you memorize this. But in here, we're more interested in seeing how a computer could compute these derivatives. So we've got around 8 minutes left. So we're gonna do this computational exercise, where the idea is that if we have some function defined in Python, and remember, you learned how to define functions on the previous lecture, we can also define a function that takes the derivative of that function, f of x, at a point x. But the thing is that to take that derivative, to compute that slope, we had to take delta x going to 0. And that is something that the computer cannot do on its own. The best the computer can do is take that delta x to be really, really, really small, but it will never be 0 itself. It cannot be 0 in a computer because we cannot divide by 0. That will be infinity, right? So we need to take delta really, 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 really small, and that's going to be an input of our function. Okay, and what is returned by this function is the change in f, which is f at the new point, x plus delta, minus f at the original point, x, that is the change in f, divided by the change in x. And the difference between x plus delta and x is just delta. This is called the forward derivative, and we're going to see that this is not the only way of implementing this. Okay, so in here in the PowerPoint, which you can see in the materials, I give you various examples of these derivatives. But maybe in order to play around with this, let me take just the last 6 minutes that we have for this hour, and let me just actually code this in real time with you all so that we can all practice together. Okay, so in here it's a notebook, and whatever I write in this notebook, I'm going to post in the course materials. So first of all, in order to do this, we have to first choose a function that we're going to be studying. So let's choose a function. Let's say let's define a function f of x, and remember that is the syntax that we use to define functions. And what that function is going to do, and I'm using Colab. I think people have been using Jupyter so far, but I think also Colab is really good, especially for this kind of settings where we're going to do very not very advanced coding, and where we don't really want the particularities of the system that we have available to impact our code. That's why we're using Colab in here. And let's choose a function. So does anyone have any suggestions for what function to study? Anyone in the Q&A or in the chat wants to suggest a function for us to study? Maybe not a very hard function. Maybe something like the sine of the exponential. Oh, arctan. Okay, so we were just asked to study the hyperbolic arctangent. Okay, that I have no idea how that function looks. So let's explore that function. Okay, awesome. I'm betting that the hyperbolic arctangent is a function in NumPy. So let's import NumPy and give it the alias NP. And we will define our function f of x to be NP arctang x. So first of all, we should just check if this computes. I don't know if that is the correct syntax for the hyperbolic arctangent. Yeah, it computed. Okay, good. And now let's build some intuition around this function by plotting it, right? So let's choose at random some values of x. And to do that, let's choose some values of x, let's say between 0 and let's say 10. Let's choose 100 values. So you have seen this function linspace. What linspace does is that it produces a NumPy array, a one-dimensional NumPy array between 0 and 10, which has 100 values between 0 and 10, and all are linearly spaced. That's how to remember the linspace lingo. And I can also define my y values in my graph to just be f applied to each of those inputs. And that is something really nice about NumPy, which is that if I try to apply this hyperbolic tangent not to a single variable x, but to a whole array of variables x, it already knows that what I really mean is apply the function to each of its entries. Okay, and return to me a vector whose first element is f of the first element of x, whose second element is f of the second element of x, and so on. So, and let's plot this function. So let's plot this function. Oh, so maybe this is not a syntax that you have seen for plotting functions before. I like this syntax, okay, where I create sort of two objects in the code. One is a figure object and one is an ax object, and they're sort of related to one another. But this ax object is the object that we're going to plot things in. Okay, so with ax.plot, we can ask it to plot x versus y. On this axis figure, we can also set the x label, for example. So we can set x label to be x. And if we want this x to look mathematical, or we want to tell Python that we have a mathematical expression here, what we can do is put dollar signs in the x. And it's always, when we write mathematical functions, we're going to have a bunch of parentheses and curly brackets and stuff. So it's always good to put a little r in front of the string, and that tells Python to be explicit about those symbols. We can also set the y label to be the function we're exploring. So in this case, it will be the hyperbolic tangent of x. And if you want that hyperbolic tangent to be nice, maybe we can put a backslash. Let's see if it understands that. And let's plot this. Oh, and I forgot to import the plotting library. So let me do that. I always do that. And here it is. That's how the arctangent looks. Do you see how this has a little bit of a corner in here? Oh, and you see that this wasn't recognized. Oh, it's because I didn't put my dollar signs to tell this it was a mathematical expression. Yeah, it doesn't recognize that expression. So, by the way, some people might know this function as the inverse hyperbolic tangent. That's another way of writing it. Let's see if that expression is recognized. Yes. Okay, good. It is plotting only between 0 and 1, which means that this hyperbolic tangent function is not defined past 1. So that is of course because the tangent function. So let's see, the hyperbolic tangent takes as a value as an input. Let's see. Let's maybe plot it all the way to 1 and see if it complains. Yeah, it has no issues. And let's plot it between -1 and 1. Yeah. Okay. Let me just real quick just look up how the function is supposed to look like. just to make sure we're getting something that is correct. Yeah, so this function has asymptotes at x equal -1 and 1. So and that's why it's complaining here. So it is not well defined as -1 and 1. So we can put it between 0.9 and 0.9, right? And we can see that it goes all the way to -1.5. What if we get even closer to -1 and 1 by saying -0.99 and 0.99? Well, you see that now it goes all the way past 2. What if we try to get even closer? Well, it goes all the way to -4, right? And to 4. And what we're saying is that really this function is exploding at -1 and 1, right? It's going closer and closer and closer to infinity. The reason is that the hyperbolic tangent, okay, there's a little bit past what we can do here. This is just a plot, and we're going to treat it as a plot. But really, the reason why this is exploding is because the hyperbolic tangent has a maximum at 1. It looks like this, and so it has an asymptote. It asymptotes to 1 as we go to infinity, and it asymptotes to -1 as we go to -infinity. So it can never go past 1, and therefore its inverse function is not well defined past 1. Okay, good. So let's take this function between -0.9 and 0.9, and we're going to try to plot the derivative of this function right here. Maybe get a little bit closer so we can see a little bit more action in this function. Okay, good. So we have a function. Whatever the function is, let's not worry too much about it. Now, we can define this derivative function, which takes as an argument, where do we want to compute the derivative at? So where in this horizontal axis do we want to compute the slope? Which function do we want to compute the slope of? And what is going to be the delta that we're going to give it to? What is going to be the change in x that we're going to use to compute the slope? And we want the delta to be really small. And as we said, what this function is going to return is going to be the quotient between the change in f. So we mean by the change in f, I mean what is f at x plus delta minus what is f at x divided by delta, right? And that will be the function, right? And now we can compute this function for our given f and our array of x's. By the way, the fact that I defined x to be a vector here and that f was this particular function here does not affect inside of the definition of this function. So whenever we put arguments inside of when we're defining a function, those arguments become local to the definition of that function, which means that it doesn't matter what the values were before. For the definition of the function is going to think that they haven't been defined before. But in here, in this block, it is going to remember what x and f were before. So now I can just tell it to compute d of x. And remember, f understands when I give for x not a single value, but an array of values of the function f that we had defined, and of a delta that I better include now. So let's choose for delta, I don't know, 0.1, small change in x, right? And let's call that dy, that list, that array, numpy array. And now we can plot it. Let me just use the coding plot that we had over here. We can plot it, but now instead of plotting y, I'm going to plot the derivative of y. And now this is not going to be that hyperbolic tangent, but it's going to be the derivative of this. So let's not focus too much on what this syntax means, but this frac, what this frac does is that it creates a fraction where the numerator is this d and the denominator is the x. So that's saying this is the derivative. Of course, it's not the exact derivative because it depends on delta. Let's see how this derivative does. So this is the derivative. So to understand this derivative, we might want to, for example, plot this function on top of this derivative. And we can do that by telling subplots that we're going to have. So let's do that on a different box. So let's plot the two things simultaneously. And what I can do in subplots is tell it I want subplots that has 2 rows. So in here, there's something really nice about Colab. It tells you what sort of parameters it can have, and it has 2. I'm going to tell it to have 2 rows, and the x is going to be the same between the two of the two plots. So I'm going to tell it that share x equals true, which is going to make the x-axis, the ticks in the x-axis, the same for my bottom plot and my upper plot. Now, what this does is that axis is no longer one axis, but it's an array of axes. It's a list of axes. Okay, there's going to be an axis for the top plot and an axis for the bottom plot. So on the top plot, x0, I'm going to plot x versus y, versus on the bottom plot, I'm going to plot x versus the derivative of y. Right, and the x label, I'll put it on the bottom plot, while the y label of the first axis is this without this derivative. Just copy this whole thing. While the axis of the first plot, the y-axis is going to be the derivative. So let's see how this plots. So now we have the two plots, one on top of the other, and we can see what is happening. Over here, the slope is positive, right? We can see that this line right here has a really positive slope, right? That tangent, and that's why this is so positive. And in fact, because this is asymptotic to minus infinity, that slope is going to get that this line is going to get more and more vertical, which means that its slope is going to tend to all the way to infinity. On the other hand, over here, we have sort of a straight line, right? We can see that the tangent, this is very well approximated by a line. And a line has constant slope. And that's why this is very much a constant function over here. And here it sort of explodes back up to being positive, right? Right. Being very positive. Okay, good. And we can do this for several functions, and that is what I did in the sorry. What do I want to do? I want to stop sharing, and that is what I did over here in the slides. So this is an example, for example, for the sine function. And for the sine function, this is the derivative computed for various values of delta x. So you see, if, for example, if I choose delta x equals to 10, I just get this wave, which is not a sine, either a cosine, because it doesn't have the right amplitude, right? It has a very small amplitude. So it's very far off from being the correct derivative. But as I lower it to 1, then this starts looking more like the actual answer. And when I take 0.1, it becomes this green line, which is almost imperceptible because it's covered by a red line, where the red line is the actual correct answer, is the cosine of x. So we see that as we lower delta x, the answer goes to the cosine of x, which is what we were expecting. And in here, I did this also for the exponential function, for the logarithm function, and for this very special function that I like to call the hat function, because it kind of looks like a sombrero kind of hat. You can see it, and this hat potential actually has to do a lot with the Higgs mechanism for the people that are interested in particle physics. And we can compute its derivative, and the same thing as we lower delta x. So for delta x equal to 1, we're very off, but then the rest of the values are really close to the correct value, which is this this purple line. Okay, so maybe this is a good point to stop for today. I am correcting that this is supposed to be only an hour long, right? So I'm already 10 minutes overboard. Is that correct? Yeah, okay, awesome. Great. So maybe we can stop now. And what we're going to do on Friday then is going to study how this convergence works for derivatives. We're going to see some better ways of computing this derivative. And then we're going to do a little introduction to integral calculus. And we're also going to see some applications of differential calculus as well. Okay, great. So maybe now would be a good time to see if there are any questions that people would like to ask.